Welcome back. In this week, we're going to discuss the topic of factoring what are known as trinomial expressions. And we're going to be focusing in on mastering two new techniques, one being what is called the guess and check method for trinomials. But then what we're also going to do is we're also going to look at applying factor by grouping for trinomial expressions. And so we'll see what that means here in a second. Let's just recall what we learned last week. Last week, we learned about two different techniques for factoring certain types of polynomials. We learned about the GCF technique, and we learned about the factor by grouping technique. Both of these techniques are very, very basic ideas that exist in the theory of factoring polynomials. And so it behooves us to understand just the basics. And what we said was the GCF technique is a very broad technique that's going to come up in literally every single math class from this moment in time until we go into our business calculus, and we're going to see even in our business calculus classes, we're going to have a GCF technique where we have to factor by grouping. Or if we go into nursing and have to take a calculus class there, we're going to see that, factoring by using the GCF technique will indeed appear. When we get to college algebra, there again, we're going to see that there will be problem statements where we need to use the GCF technique. So this is a very, very basic technique, and it keeps popping up literally in every math class. And what we're looking for when we factor using the GCF technique is we're looking for a very specific setup. Okay. Usually, what needs to set off red flags in your mind is that you have some sort of a common variable between all of the terms which may be added or subtracted from one another. So in a simple case where there are, say, two terms, you might have, say, in descending order, maybe a p squared and a p, an x squared and an x, a z squared and a z. And that would be a very, very basic instance where, red flags should be going off in your mind, and you think to yourself, this is probably where I need to use a GCF technique. The second thing that we're looking for when we use the GCF technique is we're really looking for terms that can divide evenly into one another, or terms that perhaps have a common factor between one another. One of the reasons why we drill prime factorization into the student's mind is that prime factorization is going to get us used to looking for terms that might divide a sequence of other variables or values that exist in an expression. And so it behooves us to go back and practice finding common factors using the GCF technique, or go back and practice utilizing the prime factorization technique, because the better you get at doing that, that is one of those basic core skills, the better you are, the more capable you are of solving these more challenging problem statements. So in the instance of utilizing the GCF technique, what we know is that you're going to list out the prime factors of each of your terms. So in this instance, 2p squared, for example, can be listed as 2 times p times p. We're going to give ourselves a table. We write GCF above it. And then for the term 4p, we'll just write 2 times 2 times p. Now in our table, what we're going to do is we're going to cross out common terms, common factors, and write them once in our table. And you'll see that we've got a 2 times p that's in common between these expressions. Now what that says to us is that because factoring is like distribution in reverse, the common term 2p may be written out in front of a sequence of parentheses, and then you just have to write whatever you have left over. So in this instance, we have a p left over and we have a 2 left over, so we'll write a p plus 2 inside of our parentheses. Now, while this is all well and good, it is a very powerful technique that can be used for many, many instances and many different problems. There are, in fact, problems where the GCF technique is going to fall short. A problem such as 5x minus 5y plus 4bx plus 4by is going to be an excellent example of where, say, the GCF technique falls short, but perhaps where the factoring by grouping technique is going to be what we need to use in order to find a solution. Now, one of the things you should know about factor by grouping is that factor by grouping is best used whenever you've got an even sequence of terms, say 4 terms or 6 terms or 8 terms. That's usually going to be where you want to factor by grouping or consider factor by grouping. And when you only have 2 terms, that's probably going to be, if there are factors at all, you're going to be using, say, the GCF technique. In some trinomial expressions, you can also use the GCF technique as to finesse the expression at the beginning. But then you'll have to use a more involved technique in order to actually find the factors, if it's even possible to do so. In this instance, when we're looking at factor by grouping for 4 terms, you'll see that 2 of your terms have x's that are in common, and 2 of the terms have y's in common, and then 2 of the terms also have a common b. Then you'll note that the numbers themselves have similarities with one another. That should send red flags off in your mind in order to begin thinking about maybe utilizing the factor by grouping technique in order to finesse this equation. Now, one of the things that you could do right off the bat is pull out the common factor 5 and perhaps think about pulling out the common factor 4b from these two expressions. And you'll see what you're left with are an x minus y and an x plus y. And what we said last week was anytime you are left with 2 different factors where the only issue is simply one of the factors may need and I'm sorry, I actually wrote this down incorrectly. This should have been a negative bx. What we said last week was that anytime you see 2 factors, or perhaps the only thing that you really need to do is switch the signs, say from a negative to a positive, or switch the signs on a single variable. We said that that would be an instance where one might consider factoring out a negative. And so if you factor out a negative, i.e. you switch the sign of, say, the 4b from a positive to a negative, then what happens is that all of the signs inside of your parentheses flip, and you're left with x minus y. And of course, in our last lecture video, we went through the exact reasons why this occurs. So you would have now a perfect setup, 5 times the quantity x minus y minus 4b times the quantity x minus y. And since now you have x minus y terms in common, by the GCF rules, your common term can go out in front, and what's left over, the 5 and the negative 4b, can go inside of your parentheses, and this is your answer. Unfortunately, this week, we will be dealing with polynomial expressions, which are not going to be amenable to either the GCF technique or the factor by grouping technique. Consider, for example, the expression x squared plus 4x plus 3. You'll note that while there is an x term that is in common between the front 2 terms, the first 2 terms on the left, that doesn't matter because there isn't an x term that happens to be next to this 3. Another thing to note is that the numerical terms themselves, 3, for example, doesn't divide 4, and there isn't even a number in front of your x squared term to begin with. And so at first glance, this particular polynomial appears as though it's not going to have a solution. In fact, it will indeed be factorable, but we're going to need to use a new method, which we call the guess and check method. Now, the guess and check method, similar to the GCF, is going to be one of those methods where we just need to memorize the procedure. This is going to keep showing up in every single math class from Math 950 onwards. And so it behooves us to really, really understand what's happening inside of the mechanics of this technique. What's going on when you find the factors of a trinomial. If you have a generic trinomial x squared plus, we'll call this a bx plus a c. This is our generic trinomial. Is that when we go to factor this, we're going to be left with two binomials of degree 1, where you'll have an x plus p multiplied with the quantity x plus some variable q. Now, p and q can be any number, okay, any real number, and they could be positive and negative real numbers. Don't let the addition sign fool you. P and q can be anything. So what we're going to try to do here is when we are factoring this x squared plus 4x plus 3, what we're going to do is we're going to look to see if there's perhaps some sort of a pattern that emerges in the numbers between the solution, meaning x plus p times x plus q, and the original trinomial, in order to infer whether or not there's some sort of a way we can jump from, say, x squared plus 4x plus 3 to its solution. Examining x plus p times x plus q, we're going to go ahead and use our extended distribution rule. We're going to take x, we're going to multiply it by this entire term x plus q, and we're going to add it with the term p, which will be multiplied by the entire x plus q quantity. You'll have x times x and x times q. You'll have p times x times p times q. Note that by the definition of exponents, x times x becomes x squared. You're going to have an x times q plus x times p if we use the commutative law to switch the order of our terms. I wrote a q, I need to write a p. And you'll have a p times q. Now we're almost finished with this proof. So what we're going to do is we're going to use the GCF technique to take out the common factor x, leaving q plus p. And we're done. So what we've just found is that when you have a generic polynomial expression, x squared plus bx plus c, this b term, this middle term, is actually a term that's generated, that's created from adding two special numbers, q and p together. And it turns out that the middle term's q plus p is related to the last term c, because c has to be the product of p times q. So if we find the factors of c, if we find the factors of the last term, we have all the different options of p times q, and we just have to then figure out how to add those p and q terms together to get our middle term, b. All right, let's see how this works. So we're going to use this x squared plus 4x plus 3 as a demonstration for how the guess and check technique works. Step 1 is we are going to factor the last term of the trinomial. Okay, that's always what we're going to do for the guess and check method. We will factor the last term. In this instance, we have a 3. So we're going to find the factors of 3. Well, it turns out 3 is prime, so finding its factors is fairly trivial. The factors of 3 are just 3 and 1. All we have to do then is check to see if the factors add to the middle term. That's it. So you found the factors of 3 are 3 and 1. So then you just take 3 and 1 and you guess. You see, is it the case that 3 plus 1 gives you 4? Obviously, that's true. So what does this tell you? This says that x squared plus 4x plus 3 has to equal the following. It has to equal x plus 3 times x plus 1, where this 3 and 1 come from the factors 3 times 1. And actually, to be specific, they come from the fact that these are the terms that are added to get the middle term 4. Okay, let's do another example. How the guess and check technique works. All right, let's take x squared plus 7x plus 12. And let's try to find the factors of these. Now, step 1 is we're going to take the last term, 12, and we're going to find its factors. In this instance, there are a bunch of different factors for 12. Note that you also have to include the trivial factors 12 times 1. Anything times 1 is that something. So one of the factors of 12 will be 12 times 1. Just don't forget that. A lot of students forget it. But yeah, you have a number of different possibilities. You have 3 times 4. You have 12 times 1. 6 and 2 are also factors of 12. So you have to list out all of the factors. And then step 2 is you have to check to see if the factors add to the middle term. Okay, that's all you have to do. You have to check to see if 3 plus 4, is it the case that this adds to 7? You have to check 12 plus 1, does this add to 7? 6 plus 2, does this add to 7? And you kind of just go down the list. 3 plus 4, this gives me 7. Okay, so this is good. But you'll note that 12 plus 1, that doesn't add to 7. And 6 plus 2, that doesn't add to 7. So then the conclusion is simply x squared plus 7x plus 12. This has to equal exactly x plus 3 times the quantity x plus 4. Okay. Now, if only all of these problems were so simple, if only all of the problems were so straightforward, we would be great. But unfortunately, it's not the case. You are, in fact, going to be throwing some curveballs. So consider, for example, p squared minus 11p plus 24. And we're going to try to find the factors of this particular quantity. Now, the first issue that we have, if students didn't catch it, is that this b term, originally the b term was positive. Now our b term is negative. This is just going to present a slight nuance to what we're going to do in step number 2. Regardless of our a, b, and c terms for our trinomial, we're always going to take, as a step 1, we're going to take the leading term and we're going to try to find its factors. So in this instance, you'll have 24 and 1, you'll have 12 and 2, you'll have 6 and 4, you'll have 8 and 3. All of these are potential factors of 24. Now note, though, that for step 2, you got to add to middle term. And your middle term happens to be a negative 11. So the problem here is that 24 plus 1, that doesn't equal negative 11. 12 plus 2, that doesn't equal negative 11. 6 plus 4, that doesn't equal negative 11. And 8 plus 3, that doesn't equal a negative 11. That's an issue. That's an issue. But note, 8 plus 3 does equal 11, a positive 11. And it would be great if we had a negative 8 and a negative 3 to play with, because negative 8 and a negative 3 would indeed give you a negative 11. Conceptually, this is what's going on, guys. When you find the factors of 24, and the middle term happens to be negative, you're going to have to make a slight adjustment. You're going to have to remember that, yes, while all the positive factors are not going to add to that middle term, it's possible that if you change the sign on both of the factors, note that a negative and a negative will be a positive, it's possible that one of these factors will indeed add to that middle term. And in fact, negative and negative is a positive. So negative 8 times a negative 3, that is a hidden factor of 24. We usually don't think of factors, especially prime factors, as being potentially negative numbers. But it is in fact the case that if you permit negatives, then you have a bunch of hidden negative factors that would be equivalent to any given expression that you might be dealing with. All right, so what is the conclusion that we can draw from this particular problem? So first of all, we need to check to see if we have negative factors that are potentially in play. In this instance, you'll note negative 8 plus a negative 3 was indeed equal to a negative 11. In general, you're going to have to check all of the possible negative factors to see and make sure that you're not missing one of the factors. These are easy problems, so it may become apparent to students what the factors happen to be. But when we look at more advanced problem statements in, say, Math 1100 and later, perhaps next week, that won't necessarily be the case. From what we found out, in this instance, we had negative 8 and a negative 3 that add to negative 11. What this implies is simply that p minus 8 and p minus 3 are going to be factors of the trinomial. So whatever the sign happens to be of those specific factors, whenever you're adding them together, that is going to be the sign of the term inside of the parentheses. All right, now let's look at another example. In this instance, you've got a z squared plus 3z minus 28. And the question is, what are the factors of this polynomial expression? Step one, what we're always going to do when we have a trinomial expression is we'll take the last term and we'll try to find its factors. Note that in this instance, pretty straightforward. 28 is the same thing as 2 and 14, 28 and 1, 7 and 4. And I think that's pretty much all of the factors of 28. What a student should note, however, is that in this instance, we're not dealing with a positive 28. We're actually dealing with a negative 28. So instead of having positive factors, because you're dealing with a negative 28, a 2 times 14 won't actually produce a negative 28. But a negative 2 and a positive 14 will produce negative 28. Negative 14 and a positive 2 will produce negative 28 as well. And then a negative 7 and a 4 produces a negative 28. But a negative 4 and a positive 7 will also produce a negative 28. Now with this information, we have to add to the middle term. So we're going to take our factors, negative 2 plus 14. We're going to check to see, does this add to the middle term 3? We'll check negative 14 plus 2. Does this add to positive 3? We're going to check negative 7 plus 4. Does this add to a positive 3? And we'll check negative 4 plus 7. And we'll ask ourselves, does this add to a positive 3? Now, in each instance, by process of elimination, you should be able to find that negative 4 plus 7. If I owe you $4, but I have $7 in my bank account, when I go to pay you back, I will have $3 in my bank account. And so negative 4 plus 7 is the only way we can add to a positive 3. And what this tells us is I need to have an x plus a negative 4 and an x plus 7, or said another way, I need to have an x minus 4 as one of the solutions and an x plus 7 as the other solution, as the other factor rather, for this particular expression. And that's all we're going to do. Now, it turns out to be the case that there are some trinomials that we may be presented with which don't have any possible rational, what's called a rational factorization. They don't have rational roots, so they won't have a rational factors, which means you can't break open the polynomial expression and find two values that could, say, multiply together in such a way to where those factors will nicely create some sort of an expression. Y squared plus 10y plus 12 happens to be one such trinomial where if you perform factorization of it, you're not necessarily guaranteed to have rational roots. And so what this is going to look like is just as we were doing before, we're always going to start with taking the last term, in this instance 12, and finding the specific factors of the last term. Now you'll note that 12's factors are 6 and 2, 12 and 1, and 3 and 4. But you could have also taken the negative components of those factors, since negative 6 and negative 2 will also add to 12. Negative 12, negative 1 will multiply to be 12. And negative 3 and negative 4 will multiply to be 12. Not add to 12. I think I said add to 12 earlier. I'm saying multiply to be 12. Now, if you took any of these factors, you'll note that 6 plus 2, that doesn't equal a positive 10. 12 plus 1, that doesn't equal a positive 10. 3 plus 4, that doesn't equal a positive 10. So all of these factors on this side are totally meaningless. But then if you have a negative 6 plus a negative 2, that doesn't equal a positive 10. Negative 12 plus a negative 1, that doesn't equal positive 10. And a negative 3 plus a negative 4, that also doesn't equal a positive 10. And so you're in trouble. What you're dealing with is what is known as a prime polynomial. If the polynomial has real roots, meaning a real solution, you may find the real solution using what is called the quadratic equation. Recall the quadratic equation from your high school? The quadratic equation looks something like this for any arbitrary polynomial expression, ax squared plus bx plus c. If you have a trinomial expression of degree 2 that has the following setup, in this instance, we have a y squared plus 10y plus 12. Pretty much the only thing we can do once you find that you've got a prime polynomial is you can try to use the quadratic equation in order to find its roots. And then you can do some finessing from there in order to find the factors of the polynomial expression. But this is a little bit above the scope of the course for now. Okay, because we would have to know how to, say, manipulate square root operators and whatnot. And while it's not too difficult to do that, it's just, unfortunately, it's not part of the curriculum, so we have to let it go. Okay, so while this is all well and good, we will in fact face instances where there are factorable polynomial expressions, but we just can't use the guess and check method in order to factor those polynomial expressions. And so what this is going to look like is it's going to look like something where you have a setup ax squared plus bx plus c, such as, just to give you an example, 2x squared plus 3x plus 1. Now note that 2x squared plus 3x plus 1, this is a trinomial expression because there are, on the one hand, 3 terms. But note that 2 doesn't divide 3, and 2 doesn't divide 1, and 3 doesn't divide 1. So there really isn't a GCF that you can, say, factor out of the trinomial expression itself. And of course, this particular trinomial doesn't fit the general pattern that we had here, where you've got an x squared term with a bx plus a c. Note that there's no term, there's no coefficient. There does not exist a coefficient in front of your x squared value, whereas here you have a 2 that's in front of your x squared value. That's critical for the guess and check to work, that you ensure that there isn't a term in front of your x squared. And so the question is, what are we going to do with 2x squared plus 3x plus 1? And the answer is we will turn to factor by grouping for trinomials. And this is kind of a last-ditch effort to factor a given trinomial. Like, if you can't use guess and check, then try factor by grouping for the trinomial technique. And then, if both of those fail, that's where we pretty much bust out our quadratic equation. And of course, when we go into our pre-calculus classes or our college algebra classes, or in fact, our calculus classes, when you're factoring these trinomials, you'll probably always just rely on the quadratic equation, since it's the most versatile way to find the factors. But nevertheless, how the factor by grouping technique works is that it's rather similar to the guess and check method. You're going to, first of all, multiply the first and last terms together. So in this instance, we have to take 1, we multiply it with 2, and we find out what that happens to be. Step 2 is very similar to before. What we're going to do is we're going to find the factors of 2 such that it adds to the middle term. And where did the 2 come from? It came from multiplying the first and last term together. So we're going to take our a times our c, whatever that value happens to be, and then we perform factorization of that value. And what we're looking for is we're looking for the terms to add to the middle term. Once you've done that, your conclusion is that you can rewrite, in this instance, 2x squared plus 3x plus 1 as the following problem. But what you'll note here is that now we have 4 terms, and so now we have the perfect setup for factor by grouping. So what we're going to do now is we're going to look at the terms that are in common in the expression. You'll note that by prime factorization, you've got a 2 times x, a 2 times x, a 1 times x, and a 1. You have a 2 times x in common here, a 1 in common here, and so you may pull out your common term and write what remains. Now note, when you pull out a whole term, such as 2 times x, it's not that the 2 times x is being eliminated from your expression. It's that when we do distribution, when we decide to distribute the factors once again, we need to arrive at 2 times x. Okay, and so when we write this 2x here, we got to include this plus 1 to account for the fact that what we're doing really is we've got 2 times x, that if we had done distribution law, we would have 2 times x, which is this first term, and then we would have 2 times x times 1, which gives us the second term, 2x. All right, and similarly, when we pull the 1 out of the 1, note that we can do that because 1 times 1 equals 1. So what are you left with if you pull the 1 out? Well, you have 1 left over. Now, what this tells us is that by factor by grouping, you've got an x plus 1 in common here. You have an x plus 1 in common here. You might write x plus 1 down below. In the terms that are remaining, the 2x and the 1, you need to write inside of the parentheses. And that's your answer. Okay, let's look at a more challenging case. Let's look at the case of 3x squared plus 14x plus 15. What is this going to equal to? Well, just like before, your leading term is in fact a number, not just one, a number greater than 1 in this instance. And while 3 does indeed divide 15, 3 doesn't divide 14. And so we can't just take out some quantity and put it out in front and say reduce our more complicated looking expression to something that would be amenable to the guess and check method. So what we're going to do instead is we're going to assume this is a trinomial that would be factorable by using the factor by grouping technique. That's going to be our assumption. We don't actually know, but we're going to assume that it is the case. We'll take our first term and our last term. We need to multiply those together. 3 times 5 is going to give you 45. Step 2 is you're going to find the factors of 45. Clearly, one of the factors would be 45 and 1. One of the factors will be 3 and 15. But there are going to be also other factors available to you. Note that by prime factorization, we can find the factors. You know that 45 is going to equal 3 times 5 times 5. So if you pull a 3 out, the other remaining factor, not 3 times 5 times 5, I'm sorry, it should be 3 times 3 times 5. Because you've got, I'm sorry, I'm going a little bit fast. This 45 is the same thing as 3 times 15, but 15 is the same thing as 3 times 3. Okay, there we are. So then 45 could be rewritten as a factor diagram as 3 times 15, but 15 itself could be 3 times 5. And so if you do a little bit of a rearrangement on the factors, 45 is also the same thing as 9 and 5. So 9 and 5 are going to be one of the factors of the expression. And I think that's pretty much it. Other than 45 and 1, you got 9 and 5 and 3 and 15. Okay, so that's step 2. But we need to use this information to see what adds to 14, to the middle term. And so we're going to ask the question, 3 plus 15, does this equal 14? Of course, that's a no. 9 plus 5, does this equal 14? And 45 plus 1, does this equal 14? Now, what we do with this information, now that we found that 9 plus 5 is equal to 14, is this tells us that 3x squared plus 14x plus 15 is equal to 3x squared. You'll note that 3x squared doesn't change. You'll note that the last term, 15, doesn't change. And all we're doing is we're actually breaking open this 14x, and we're rewriting 14x as the sum of two smaller terms so that we get the factor by grouping setup that we like so much. This is going to take a little bit of practice for students to write it in the way that makes factor by grouping easiest. And in some instances, this is just going to fail, okay? So in the instances where it fails, there are things we can do. I'll show you what those are in class, but for now, my recommendation to students would be to just repeat the problem and maybe change the order of your terms. So if I found, say, that 3x squared plus 9x plus 5x plus 15 didn't work, then I would switch the order of my middle terms to see if I could get a better setup for the factor by grouping technique. Now, because I've done this so much, I could already tell that I needed my 9x to be parked next to my 3 because 3 divides 9. So we can go ahead and for our next step, we'll use prime factorization on all of these terms so that hopefully students can start seeing what they have to work with. And by prime factorization, 3 times x squared is the same thing as 3 times x times x. By prime factorization, 9x is the same thing as 3 times x. 5 times x is just 5 times x. And 15 is the same thing as 5 times 3. So, looking at the terms that you have in common, you've got a 3 and an x, a 3 and an x. Let's put the 3x outside. And then what goes in the middle is what's remaining. So you've got an x left over and a 3 left over. Now for the second two terms, I'm going to check and you see you have a 5 in common. And you have an x left over and a 3 left over. So you're going to write that inside of parentheses. Note that all I'm doing here, guys, is I'm kind of doing a shortcut for finding the GCF. So if you have 3x squared and 9x, and we find the GCF of these guys, note that we're expanding the terms by prime factorization, and then in a special box, you write the GCF of the terms. And that tells you what goes outside of your sequence of parentheses. And then what this x plus 3 happens to be, where that comes from, is that's going to be the remaining terms that exist once you pull out the 3x. Or said another way, it's going to be the terms that you didn't cross out when you were locating your GCF. And the same is true for the 5x plus 15. If you wanted to calculate the GCF of the last two terms, you have 5x, which just is 5 times x. 15 is 5 times 3. So when you're calculating that GCF, you're crossing out your 5s, you're writing that in the box once, and you've got an x and a 3 left over. So that's kind of what I'm doing. When you get a bit faster, you don't necessarily have to use the box technique in order to find your GCF. You can just kind of see it with your eyes. And in fact, a lot of students who are pretty quick, they're going to be able to see the factors with their eyes just right off the bat. When in doubt, go back to using the more involved but correct techniques, if that helps you out. But most students just need some practice. By factor by grouping, we found that there exists an x plus 3 in common, and so you may write the x plus 3 on the right, and then whatever is left over. In this instance, you've got a 5, so you write a 5 in your parentheses on the right, and you got a 3x left over, so you write the 3x in parentheses on your left, and you're done. These are your factors. This is your factorization. One last example, and we'll call it a day. Let's look at a nastier one. This one looks absolutely dreadful. Let's look at 12x squared plus xy minus 6y squared. Now, naturally, alarm bells will be going off in the minds of students because this trinomial doesn't even necessarily appear like an ordinary trinomial expression. On the one hand, you've got a 12x squared on the left, but you also have a negative 6y squared on the right. So initially, a student might think, well, because I've got a common x term and or a common y term, that might be a factor by GCF strategy. There may be some sort of factor by GCF technique that I could use here. But of course, the problem is you only have 3 terms, and the third term doesn't have a common value. So GCF won't work. Fortunately enough, you can in fact use the techniques for finding a factor by grouping setup using the following strategy. So the first step is we're always going to take, say, our last term, the first term, 12, and our last term, negative 6. And what we're going to do is we're going to multiply these in common. Now, unfortunately, what's going to happen is negative 6 and 12, that gives us a negative 72. So right off the bat, we're dealing with this number that's pretty big. And so for step 2, the only thing we really have to watch out for is we need to really be careful that we're accounting for all of the possible factors of 72. So when we look at 72, you'll note that 72 is the same thing as, say, 72 and 1. So you might have, say, a positive 72 and a negative 1. You may have a negative 72 and a positive 1 that would multiply together to get 72. Now, there are, of course, other factors. 36 and, say, negative 2 would give you 72. Negative 36 and positive 2 would give you 72. Let's see, 24 and negative 3, I think, would give you 72, but then negative 24 and positive 3 would also give you 72. Of course, we said 12 and negative 6 gives you 72, so a negative 12 and positive 6 will give you negative 72. And then don't forget 9 and negative 8, as well as negative 9 and positive 8. All right, so there are a lot of factors, but the good news is we're adding these factors to the middle term. You'll note that the middle term is just an x times y, and anything by itself is 1 times that something, so it's really like we're adding to positive 1. Hopefully you guys can see that 9 plus negative 8, that is indeed going to give us a positive 1. But if you didn't see that, you're going to have to check each one of these factors, okay? So what is the conclusion that we may draw from finding that 9 plus a negative 8 gives you a positive 1? Well, it means that we can break open this 12x squared plus xy minus 6y squared. And we can rewrite this as 12x squared plus 9xy minus 8xy minus 6y squared, just like that. And once we do that, of course, making sure that we're lining ourselves up for a proper setup to begin with, what we're then going to do is we're going to use some prime factorization. So we're going to need to find the prime factors of 12. 12 is the same thing as 3 and 4. X is the same thing as x and x. 9 is the same thing as 3 and 3. 8 is the same thing as 2 times 2 times 2, or 4 times 2. And actually, I'll probably just leave it as 2 times 2 times 2 for now. I don't know if there's a pattern that I'm specifically looking for. So when I don't know the pattern that I'm looking for, it's best to just write everything out in its most simplified form. Now, you've got a 3 that's in common between these terms on the left. You also have an x, say, and an x that's in common. And I think that's pretty much it. So let's go ahead and we'll pull out the common terms by the GCF rules. And then we write whatever is not in common, the 4 and x, for example, and the 3 and y. That's going to go inside of our parentheses. Now, the only thing that's a little bit weird is we do have to watch out for these negative signs, right? But because the negative signs are in common between these two terms, I could pull out, say, a negative 2 and an x. Maybe. No, I can't pull out an x. I could pull out a y, though. And then once we pull out those negatives, you'll see that you're left with a 2 times 2, x, and 3 times a y. Noting that once you pull out a negative 2, negative times a positive is a negative. So you've pulled out the negative component, meaning that your terms in the parentheses need to be positive. 2 and 2 is 4, so let's go ahead and we'll clean this innermost parentheses up a bit. So you're going to have 4x plus 3y times the quantity 3x. And now our factor by grouping setup is almost complete because you see you have 4x plus 3 y in both instances. It's a good way to check that you have not made a mistake. You may write these terms like so and circle it. This is your answer. And that's your answer. Solution. That's all. That's all you have to do. And this is about the hardest and or most challenging problem that I saw in the chapter. And so I think you guys are prepared. You're ready to try some on your own. And as always, if you have any questions, reach out to me over email and or come into my office hours. I will see you guys next class. Take care.